So we have this formal way, these activity coefficients and activities, to take into account non-ideal behavior, but how do we actually find these activity coefficients? Or else they're kind of useless if we can't find values for them. So one way, of course, is to do it experimentally. You know, if we can measure a bunch of different concentrations, we can figure it out. But a couple of chemists, Peter Debye and Huckel, I can't remember his first name now off the top of my head, came up with a theory that takes this idea of ionic atmospheres into account. And basically this is based on experimental data, but they came up with a way to take into account this non-ideal behavior of ions to come up with a way to calculate activity coefficients. So this works for dilute solutions. As they get not dilute, things get worse, and this theory doesn't really work. The assumptions underlying it break down. And we're not, in this class, going to talk about the assumptions. We'll just talk about sort of the implications and look at a couple of practical examples. And so this works to mu of about 0.1 molar. Mu here again being the ionic strength. So as things get pretty concentrated, this theory breaks down. So the equation that's the result of the theory, is that the log base 10 of the activity coefficient is equal to a bunch of constants that are all wrapped together in this negative 0.51. Z squared, Z is the charge of the ion, the square root of the ionic strength divided by 1 plus a fraction here, alpha times square root of mu again, square root of the ionic strength divided by 305. Okay, so we won't be using this equation much, but just to sort of show you what we're thinking about here, what goes into this theory, right? The things that matter. That's really what I want you to see from this. Mostly we'll just use values that have already been computed for ions that we care about. But we can see that there are a few things that matter that will affect the ionic strength. Not the ionic strength, the activity coefficient. One is the ionic strength. And let me just, again, reiterate what all these mean. Gamma is the activity coefficient. And this is what we'll multiply by our concentration to give us the activity. Mu is the ionic strength, which we've already defined. And alpha is, that's the one thing I haven't defined here. Alpha is, and I'm putting this in quotes because it's only very approximately, the ion size in picometers. And this is really, in reality, this is more of a fudge factor. This is, you pick the size that makes your data fit the experimental evidence. And the last one, Z, is the ion charge. Okay, so I want you to pause the video, look at this equation, and see what matters, right? What are sort of trends that you think, trends that you can see mathematically as we change, say, mu, Z, and alpha? Okay, hopefully you paused the video, took a minute to think about it. Right, so one thing we see is that as Z increases, the log will also increase, and what that means, or the log will become more negative, that means that our gamma value will decrease, right? So it'll be further away from 1, basically. And this is what we'd expect. Larger charges, whether positive or negative, it doesn't matter because it's squared here, should lead to a more significant deviation from ideal behavior. Okay? So the other thing we could see here, though this one isn't as obvious because there's a mu on the top and a mu on the bottom, but as mu increases, the activity coefficient will also decrease. So as more ions are in solution, even if they're not the ions that are part of your equilibrium, the effective concentration will decrease, right? So the activity coefficient decreases. And another one is that as alpha increases or decreases, gamma will decrease. Now, a little bit easier way of seeing this is in your textbook. Let me just pull this up here. There is actually a chart here of activity coefficients for various ions. Now, this ion size is just something you have to look up. It's not something you can find, calculate. So we can see different ions have effective ion sizes, and this is why I put it in quotes. If you see, for example, H plus is the largest ion, which makes no sense because it's a proton, right? So this is this is sort of a fudge factor, right? Many of these other things are large ions, right? I think, these organic, many species part of them, right? Many things part of them, but this is an effective thing. And then we can see ionic strength increasing here, and these are values from the formula that I just showed, right? So these go up to about 0.1 molar ionic strength. And we can see, values close to 1 as the ion size is bigger. But as we increase the ionic strength, they become further away from 1. And as we go down to a plus or minus 2 charge, we can see these values are significantly smaller than the values for the plus or minus 1 charge. And the plus or minus 3 charges down here are even smaller. And then we have a couple of plus or minus 4 down here. And you can see these are very far away from 1, even at very low ionic strengths. So that's a little bit about ionic strength and activities and how they're related to each other and how we can use Debye-Huckel theory to get some specific values.